can be described by the pure excitation, the pure emission spectrum and the pure excitation spectrum. And that means if I'm only measuring this one, I can actually describe the contribution as the outer product of the excitation spectrum and the emission spectrum. And that's a shape like this. And see how it has the same shape in this direction and the same excitation shape in this direction. So when I change the concentration, the shape doesn't change at all. It still looks like this from the excitation, and it looks like this from the emission. And that's crucial. That's Beer's law. Beer's law states that when I change the concentration, the spectrum, the shape of the spectrum does not change, only the magnitude. And that's what we're using here. Also, as I showed you yesterday, for many samples, well, I can describe every sample using Beer's law, using the pure excitation and the pure emission spectrum, and just by multiplying with the pure concentrations. So in this sample, we only have the blue, so I just multiply the other ones, the other two, by a 0 concentration. And here's a completely different sample, but I'm still going to use exactly the same shapes. Now I'm just going to multiply the green and the blue one by 0. So no matter what combination of these three chemicals I have, I can always describe them by the same excitation and emission spectrum. And that's perfectly fine. And stop. Here we are. Let's see. No, come on. Now the real magic here is that if I take these 5 samples, excitation times emission, 5 samples, and put them in a box, and I fit a 3-component model, it's going to find these 3 excitation loadings, these 3 emission loadings, and these scores, which is kind of strange, but that is because Parafac does not have this orthogonality. When I do PCA, okay, this is difficult. When I do PCA like this, I have to impose that these are orthogonal and these are orthogonal. Otherwise, PCA doesn't know. There would be a different solution every time. Now it happens to be that if I have a 3-way array, there's only one. This is really complicated. There's only one way to fit a Parafac model. So I don't need the orthogonality. And that's crucial, because that means that I will actually find the real thing, not some orthogonal abstract representation, but I will find the real thing. And let me show you how that looks. So let me take a data set. Where are we? So actually here I have a 3-way data set. It's 5 different samples measured at 201 emissions and 61 excitations. And I'm sorry, I like to do things in MATLAB. So forget about what I'm doing now, but you will see the results shortly. I'm just plotting all the samples. I hope. Yes. Okay. So these are the 5 samples. So that's a 3-way array. Sample 1, 2, 3, 4, 5. So that's 5 times 201 emissions times 61 excitations. Now before we were doing PCA on this one, and that gave us strange scores and loadings. But now I want to build a Parafac model of this. And I know, we'll talk about that later on, but I know that there are 3 components, because I can kind of see that here. So I'm going to do a 3-component Parafac model. So I'm going to find 3 excitation spectra, 3 emission spectra, and then I'm going to find the score for each of them. So let me do that in this place. Let's see. Here we are. And now I want to do not PCA, but I want to do Parafac. And I want to do 3 components, and we'll talk more about how we figure out how many components to do. But let me plot. Now I have sample scores, I have emission loadings, and I have excitation loadings. Let me take a look at these ones, for example. Now this is actually very close to magic, because we just took our fluorescence data, and the only thing we said was, give me 3 Parafac components. And these are the 3 loadings in the emission mode. And they look exactly like the pure spectra of, in this case, amino acids, but that's not important here. But they look exactly as what you would expect. And also, let's take a look at, for example, oh, well, here we are. The excitation mode. They also look absolutely perfect. So, I've basically found the underlying chemical components by just saying, give me a 3-component Parafac model. So just by doing 3-way PCA, I have separated the contribution of these 3 components. So a score tells you what's the amount of the loading. So the score for sample 1, or for example the first component, will tell me how much of the blue I have. That's the concentration, because these are pure spectra. So the score now is not a abstract PCA score, it's really the concentration of the blue sample, for example. So let me take a look at the scores. So these are the scores of the first component. So these are the scores of the first component. So we have a high concentration in sample 1, and then it's basically 0 in 2 and 3, and then a little bit lower here. So now we have estimated the concentration. Look how we don't get any negative values. In PCA we get these loadings that look positive and negative, but in Parafac, because it's unique, none of these are actually negative. They negative. They all come out positive because the real spectra are positive. And as I explained yesterday, this is really chromatography. We have mathematically taken these mixtures and we have separated them into the real chemical entities. And that means that we can do a lot of things that we would otherwise not be able to do. And I'll get back to that. Okay, so we were here. So basically for this environmental example, what you have now is that you don't really have to just do peak picking. You can actually look into the real chemistry of the sample. So you can measure water samples and you can separate them into the underlying chemical components, and you can identify them and you can quantify them. And that gives you much, much better means for analyzing your data than what you would have traditionally. And it really has been a revolution in this field. So, I mean, Parafac now is the standard tool in environmental monitoring because you get much more information out. There's a lot of problems, of course, and we'll get to some of those, but you really get much more information out than with any alternative approach, you can say. So, as I told you, the reason we can do this is because Parafac has only one solution. I don't have to use this orthogonality. I don't have to enforce that scores are orthogonal to each other, because Parafac can find the real thing directly. And that's called that the Parafac model is unique. Mathematically, that means when I ask for solution, there's only one solution. And it means I can get mixes separated. It means I can estimate concentrations. Actually, you know, yesterday we also talked about that a PLS model requires many samples if I want to build a calibration model. Well, with Parafac, I can actually build calibration models with just one sample. I don't need to have many samples, even if there are interferences in your data. So I can take one pure sample of tryptophan, and that's it. That's my calibration set. And now I can predict in beer and wine and meat or whatever, I can predict tryptophan using fluorescence. I don't have to have all interferences covered, etc., like we do in PLS. So we can do a whole different kind of calibration. Now, I don't know if you can imagine, but let's say I have a matrix. Let's see how we do that. Do this. Let's say I have a matrix like this, and I want to do PCA. I call it A and B. Like this. These are the residuals, what I'm not describing. Now, I told you that these components are orthogonal, and also these ones. They have to be orthogonal. Okay, let's say I'm cheating a little bit. So now I'm taking the same matrix and putting it here, and another one, and another one. So it's all the same data. I'm repeating X to get a freeway array. And now I can fit a Parafac model. It would be really strange if that would work, and it doesn't. Because I don't get any new information in this direction. There's no new information being added, and therefore I don't actually get uniqueness. If I could do this, then even PCA would be unique. So it's kind of natural that this will not work if I'm just repeating the same data. So conceptually, what you have to think of is that in this direction, you have to add new information. You have to look at the data in a different way. And if we want to boil it down to something more easily understandable, let's say I'm doing A and B and C. That's what we call them in Parafac. So these could be the pure emission spectra. They have to be different. The emission spectra have to be different. Otherwise, Parafac will not work. If two of these chemicals have the same emission spectrum, exactly the same, it's not going to work. So they have to be different. That goes for the other ones as well. So the excitation spectra, they have to be different. In our case, we're estimating 3 different excitation spectra. They all have to look different. They can overlap, that's fine, that's no problem. Parafac doesn't care if they overlap or not. But they have to look different. And also, the concentrations have to be different. So if this is not fulfilled, Parafac will not be able to separate. And that can be a real problem because sometimes some chemicals are correlated. They go up and down together. It's very important when you build the Parafac model that you are aware that it has limitations. Now, if the data behave nicely, Parafac can give you these small miracles, but it can go wrong for several reasons. And one of them is that if these components are correlated, are perfectly correlated, are the same, then Parafac is not able to handle that. So think of it as that they have to be different. That's the important sort of criteria. Where did it go? Here. Now there's also a more complicated way of saying that, and I'm going to say that now. You don't actually have to listen because it's way too complicated, but it's just to show you that there's a formal way of checking whether Parafac is unique or not. And this formal rule will actually tell you that there's even more relaxed conditions. So it's not only what I said before. I said these have to be completely different and different and different. Actually, Parafac can also work under some special conditions. But it's not really important. The real important thing is to remember that if you're just replicating data or if 2 analytes are the same, it's not going to work. But I'll explain this anyway. If you found A, B, and C, we can define something called the K rank of the matrix. Now, to explain the K rank, let me show you. Let's see, we have a matrix. Whoops, stop. let's say we have a matrix like this. 1, 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5. This matrix has rank 2 because there's 2 different things going on. That's fine. The K rank is the number of columns that I can take out randomly and have full rank. So if I take out these 2 columns, it's rank 2. If I take out these 2 columns, it's rank 1 because it's the same information. So therefore the K rank of this matrix is 1. Normally the rank and the K rank is the same, but because I constructed it like this, the K rank and rank differs. Well anyway, if I take the K rank of this, this, and this, and add them together, and that number is larger than the number of components plus 2, or times 2 plus 2, then it's unique. Okay, so for example, let's say I have a 6 by 6 by 6 array. So 6 samples, and I measured 6 variables on 6 occasions. And let's say I want an 8 component model. Well, that's kind of weird. And in PCA, if I have 6 samples, I cannot get 8 components. I can get 6 maximum, but not 8. Well, Parafac is not like PCA. I can easily get 8 components. And if the K rank is 6, 6, 6, so that's 6 and 6 and 6, that's 18. 8 components, that's 16 plus 2, that's 18. So it's fine. So I can find 8 different things from 6 samples uniquely. That would never happen in two-way analysis. And it shows you that if you unfold the data, if you turn it into a matrix, you can lose information. There's no way you can find 8 different things if you turn it into a matrix. But if you keep it as a three-way array, you can find 8 different things uniquely. And that's really, really special. Okay. So let me show you what this means in practice. Let me get back to MATLAB. Let me restart MATLAB. MATLAB doesn't like when you change resolution, when you connect to a projector for some reason. Okay, so let me open the data set again. Yeah, and let me open Parafac. Today I'm not going to explain this interface very much, but tomorrow morning we have a session on PLS Toolbox, and then I'm going to explain this in much more detail. Okay, so now I estimated a 3-component Parafac model, and I get, for example, my emission loadings like this. Let me make a little drawing. So what I'm saying is that this Parafac model is unique. So there's only one way of describing these data with 3 Parafac components. Now, one thing that is very important here is that I keep saying that we can find the real chemistry in these data by using Parafac because it's unique. But the reason it really works is that this is actually Beer's law. If I ask what is the Beer's law representation of my fluorescence data, it is exactly this. It has nothing to do with Parafac, but this is just the Beer's law representation of my data. So when I fit a 3-component Parafac model, and there's only one of them, and it coincides with Beer's law, then this is Beer's law. Okay, that's convoluted, I know. But what I'm saying is, if I do a 1-component Parafac model here, so instead of doing a 3-component, if I do a 1-component Parafac model, that's also going to be unique. but it's not going to give me pure spectra, because this is not Beer's law. Beer's law of this particular data set says there's 3 components, because there are 3 fluorophores. So this is also unique. That's a mathematical thing. And let me show you how it looks. Let me do a 1-component model on this data set. Now remember that the loadings look nice and sort of almost Gaussian and non-negative, etc. So let me now do a 1-component model. Let me plot the loadings. And now it looks like this. And this is not nice. Well, I mean, if you are into fluorescence, this is not nice. This is not the pure spectrum of anything. It's more like a weighted average of all the emission spectrum. Because this is not Beer's law. Beer's law does not say that one of these can describe the data. Beer's law says that there are 3 of them. Now this is annoying because in PCA, let's say I'm doing a PCA model. Let's say I'm doing a PCA model. This is a 4-component PCA model. I hope you can see it. I'm sorry. So component 1, 2, 3, 4. Let's say that in the end I decide there's only 2 components here. So I only want to look at component 1 and 2. Then I can just look at these 2. Because even in a 4-component model, these 2 are the same as in a 2-component model, because of the orthogonality, and that's really, really nice. We don't have that in Parafac. These ones are not orthogonal, so when I want to find the model, everything has to be changed. So in Parafac,